Segment 61C, the Earth and Earth-like planets in the solar system. The solar system has in its inner zone a set of terrestrial planets, Venus, Mercury, the Earth, and Mars, and then in the outer part a series of gas giant planets, which we refer to as the Jovian planets. The planets all lie fairly close to the ecliptic plane, that is, the plane in which the Earth moves around the Sun. The tips of the orbits are only a few degrees, the major outliers being Mercury, which is closest to the Sun, and of course Pluto, which we don't count anymore, this being a fairly old illustration. The relative sizes, they're all much smaller than the Sun, and as you see, the gas giants are giants for a reason. They're very much larger than the Earth and the other inner planets. How do we determine their properties, the size, mass, density, composition, properties of the atmosphere, and age? Well, these are determined in a variety of ways. The size from the angular size and the distance, the mass from the orbits of their moons, or the deviation of the path of a satellite in the case of a planet such as Venus that doesn't have any moons, the density from the mass and the size, the composition of the atmosphere we get from the spectrum of the source, and the overall composition we can infer from the density plus a model of the structure of the planet. The properties of the atmosphere we can get from spectra. Sometimes we can also understand the properties by watching a star disappear behind and look at the absorption of the light as the star disappears behind the planet. And the age is something which we'll talk about in this lecture, how we determine that. So here are the terrestrial bodies, and they include not only the 4 planets I mentioned before, but some of the larger moons of the outer planets, in particular the Galilean moons of Jupiter and Saturn's moon Titan. The gas giants we won't be discussing in any detail today, and these are all in the outer solar system, and in many ways, because they contain much more hydrogen and helium, they're in many ways more like stars than like they are like the inner planets. Also in the solar system, we have a large number of minor bodies, including some that come into the inner solar system, and if they're icy bodies, then they form into comets, as we normally see comets, and we should be seeing some very spectacular ones in the near future. The age of the solar system is something that we get from radioactive dating. But one of the questions we have is, why hasn't the Earth frozen solid in the last 4.5 billion years? And that has to do with the radiation that is decaying, the heavier elements that are decaying that produce the radioactivity. This radioactivity keeps the inside of the Earth warm. It also provides a means of telling the age. So 2 particular decays, for example, rubidium-87 decaying to strontium-87 and potassium-40 decaying to argon-40, have half-lives that are bracketing the age of the Earth. A half-life is the amount of time it takes for half of the material in the parent sample to decay to become the daughter sample. So this decay is a random process with an equal probability in a given time interval for each atom, but statistically it all works out. So after 2 half-lives, a quarter of the material is left over, and after 3 half-lives, an eighth of the material is left over, and you wind up with a chart like this. So you start with 100% of the parent atom, and after 1 half-life you have half of it remaining. After 2 you have a quarter, and after 3 an eighth, and so on. By comparing the amount of parent and daughter isotopes, you can then infer the age since the object was last cooled down, since the object was last melted, since in a melting event the gas will escape, and so, for example, the argon disappears and it kind of resets the clock. And the formal mathematical expression of this is that the number currently over the number you had originally goes as an exponential, e to the minus bt, where b is 0.69 divided by the half-life. So we can use this formula and this technique to get the age of the Earth's crust. Meteorites will give us the age of the whole solar system when we sample a meteorite on the surface of the Earth. When we do this, we get an age for the Earth that's about 4.5 billion years. So the Earth's been around for these 4.5 billion years, and where did its current surface come from? What is it that's shaping the surface of the Earth? And there really are 4 major events that affect the surfaces of all the Earth-like planets, what we call tectonics, otherwise known as continental drift, volcanic activity, erosion, and impact. And we'll learn about these by looking at pictures of some of these bodies. First of all, let's talk about the tectonic activity. The hot interior of the Earth generated by this radioactivity has to cool off, and originally all the planets have to cool off because they start out quite hot and molten in the middle. Rock is opaque; the radiation won't carry the energy out. Rock's a very lousy conductor, so conduction doesn't do it. So the only thing that's left, as we know from our experience with the sun, is convection. But how can it work here? This is rock we're talking about. It turns out that the rock is actually fairly plastic when it's warm, and the warm material rises and then cooler material sinks back down. We see this at the Earth's surface from the mid-ocean spreading, the middle of the Atlantic and the middle of the Pacific Ocean growing wider and wider, and then what we call subduction, where the plates turn under at the edges of these zones. That leads to a tremendous amount of volcanic activity. This you can think of as the continents as being just rafts, that is to say, areas of solid material sitting on a much more fluid interior, the lithosphere of the Earth, and floating along with that. And this is the continental drift that we see. And this by looking at the geometry of the Earth, we've been able to show that over time the continents which started much closer together have moved apart and changed their configurations. And we can see this happening today. We can actually measure by using precise distance measurements the actual motion of the continents with respect to each other. Another very important activity is volcanism. So here's a picture of Mount St. Helens, a beautiful cone volcano in the Cascade Mountains, spewing ash and rock into the air and smoke just before its eruption in May of 1980. Here's a picture of the mountain today after it blew off its top, and in a very violent event that shaped that part of the mountain chain very, very dramatically. Here's a picture of West Texas, where the mountains are much, much older. The valley floor is at about 5,000 feet, and the mountain peaks are at about 6,500, so very little difference. This is an older chain which has been eroded away, leaving the hard cores of the mountain and depositing the softer material to fill in the valleys. So this is a landscape where erosion has played a major role. You're familiar with deep river valleys that were cut by erosion, but you can see erosion even in regions without deep river valleys. This, of course, is an example of impact. Because of the rapid effects of the other forces, we don't see too much of this on the surface of the Earth. This is this is the Arizona meteorite crater. So we do see some, but earlier in our history, impacts played a much bigger role in shaping the surface of the Earth. We can learn about the interior of the Earth by looking at the sound waves that are generated in earthquakes, and their behavior differs depending upon what kind of sound waves they are and whether they're passing through solids or liquids. This allowed us to build this model of the Earth with a solid mantle and a liquid interior. This is Venus, which is covered with clouds. So how can we study the surface? The answer is that we had to send a satellite there with a radar system on it that could image the surface with radar. Using that kind of imaging, we can see cracking in the crust, which is evidence for tectonic activity, and allowed us to infer that Venus has still at some point had active tectonic motion of its surface plates as well. It also has some spectacular volcanoes, and here's a picture of a double volcano on the surface and on the multiple lava flows that have deposited material across a large area of the surface of Venus. This is the moon, which actually looks very similar to Mercury, and what you see here is a surface that's totally dominated by impacts. You see impact craters everywhere, and then the large mare that you see there are actually due to large impacts in the later part of the formation of the solar system that broke through the early crust of the moon, and upwelling of lava then smoothed out the surfaces over these regions. So the older areas of the surface are the rough areas where there's still a lot of impact sites left, and then the smoother areas are where new surface formed, and then there weren't so many impacts after that surface formed. Mars, we've actually studied very, very thoroughly. From the surface of the Earth, you can see the polar caps, and some modeling of the surface, but you can't really investigate it in any detail. You need to send satellites closer by. So here we've sent them very close by. Of course, we've landed a number of landers on the surface and image details about the geology of the surface of Mars and looked for the effects of water in an earlier epoch. I'm going to show you just essentially some aerial photos from orbiters of the Martian surface. So here's another example of crustal cracking showing earlier tectonic activity on Mars, which we think has subsided as the interior of Mars has cooled over the years. This is a picture of the south polar cap, which has both water and carbon dioxide ice in it. Here's an example of sand dunes, which we believe are indicative of actual wind erosion. Mars has a thin atmosphere, but it does have storms and winds that can move these sand dunes around. Here's a picture of clouds in the Martian atmosphere showing you the existence of this atmosphere. These clouds are made of, unlike on Earth where cirrus clouds might be frozen ice crystals, these are frozen carbon dioxide crystals because the atmosphere is much cooler. Here's a very dramatic picture of the edge of a long valley on Mars where you see strong evidence for erosion caused by water flow at an earlier time. Here's a picture of channels on the surface, which are very reminiscent of water flow channels on the surface of the Earth. But if you look at them carefully, you'll notice that they're interrupted in places by many impact craters. This is a sign that these flowing water happened a long time ago, because we know the impact history of the solar system, and the number of impacts has been very low in recent hundreds of millions of years. And so when you find these water channels layered with impact craters, it tells you that the flowing water occurred on the surface of Mars a very, very long time ago. Here's a picture of the largest volcano in the solar system. It's a shield volcano on the surface of Mars called Olympus Mons, surrounded by early morning fog. This again is carbon dioxide clouds, and the mountain pushes up through the fog. And what you're seeing there in the middle is not an impact crater, but a caldera like you would see on an earthbound volcano. A lot of speculation has gone into whether or not there's life on Mars, either now or in the past, and some of this has been studied by looking for life in extreme environments on the surface of the Earth, in regions where there isn't any availability of atmospheric oxygen, or the temperatures at an extreme. The evidence so far is only circumstantial that the conditions for life may have existed earlier, that Mars may have been considerably warmer and wetter at an earlier epoch. Even if you do find evidence for life, it's much more likely that you'll find very simple life rather than complex life, because it seems like there's an additional barrier in the process of developing more complex creatures beyond what it takes just to develop replicating energetic objects like single-celled animals. Here's a few examples of some of the bodies in the outer solar system. These are the 4 Galilean satellites of Jupiter. One of the most interesting is Europa, which you see on the left, which may have a liquid ocean underneath the ice layer on the surface, and people are very interested in trying to study the interior of that. One of the other very interesting satellites is Io, which is the most volcanically active body in the solar system. The passage of the other satellites by it on their orbits torques it, because it normally keeps one face pointed towards Jupiter, and this torquing kind of kneads the interior of Io, and that keeps the interior very warm and causes volcanic activity. And you can actually see on the left side of this picture the plume of one of these volcanoes. It's spitting out gaseous sodium. That gaseous sodium winds up orbiting around Jupiter and is responsible for some of the spectacular electrical effects in the orbital region around Jupiter.